All flip-flops and flip-flop latches share the same control signals. The group of associated control signals with a flip-flop is important since only flip-flops that share the same control signals can be grouped into the same slice. This means that if you don't manage the use of your control signals and try to reduce the number of control signals your design has, then you might have trouble getting high device utilization. The set and reset signal can be configured as synchronous or asynchronous. For synchronous design purposes, Xilinx recommends that unless absolutely necessary, you design with a synchronous set or a synchronous reset. Now, we discuss good synchronous design practices in the Essentials of FPGA Design course. To help designers with this, we have made a series of Vertex-6 and Spartan-6 HDL coding style RELs. They discuss the impact of this and provide you with many good design practices that will help you get high performance and high device utilization. So check those out. Many, but not all, LUTs in the FPGA can be configured as distributed RAM. This is a small 64-bit memory that can perform a single, dual, or quad port memory. Each port has independent address inputs and has a synchronous write and an asynchronous read. There are 4 configurations, as you can see from the slide. Most customers use these resources for DSP applications. Sometimes customers try to build larger memories out of these, but it is important to keep in mind that the extra logic used to connect them together will make the performance prohibitive. So only do it if you don't care about the speed of the memory. And in general, those customers that build with this are using the core generator or system generator to build a DSP application. Also keep in mind that if you're trying to build a larger memory, it might be better to actually target the block RAM resources that are dedicated to silicon. And that is usually easily instantiated from the core generator. Many LUTs can be configured as a 32-bit shift register as well. This is used primarily as a pipeline delay element for balancing pipelined applications, but it can also be used for variable length shift registers, synchronous FIFOs, CAMs, or for pattern generators. The SRL is also cascadable up to 128 bits in length. The most challenging thing with this is that most customers don't realize that it is not loadable, has no reset, and only offers serial in, serial out capability. So if you try to infer it with any of these behaviors, your synthesis tool will instead infer regular registers, and that could be a big waste. The benefit of this resource is that it can effectively provide the work of 32 registers with a single LUT. In pipelined applications, that is a huge savings. This is an example of the use of the shift register LUT, commonly called the SRL. It can be used as a programmable delay element, or no operation or no-op. In this example, you see a 64-bit bus being processed through operation A, B, and C. A has a delay of 8 cycles, B has a delay of 12 cycles, and C has a delay of 17 cycles. Because the data processed is also grouped at its output with a multiplexer, these data paths must be synchronized, so that appropriate data is compared at the multiplexer. To do this, the SRL can be used to delay the C operation by 9 clock cycles. If we were to do this with registers, it would require 576 registers. If we use the SRL functionality instead, we only need 64 lookup tables, each programmed for 9 clock cycles of delay. So this example uses 64 LUTs to replace those 576 flip-flops and the associated routing resources to complete this. Pretty good justification for using the SRL, huh? Because there are so many registers in the FPGA, pipelining is an effective way of designing to increase design performance, because pipelines can sometimes become unbalanced when too much logic must be generated. It is necessary to delay some of the signals. One of the best uses of the SRL is to add delay to balance pipelines. So now that we know that each LUT has 3 different configurations, that is, logic, distributed RAM, and the shift register LUT, we can discuss the 3 types of slices in Spartan-6. So the SLICEM is a full slice functionality where the LUT can be used for logic and memory in the shift register LUT and has the wide multiplexers and carry logic associated with it. And this is 25% of the slices in your device. The SLICEL supports logic and arithmetic only. The LUT can only be used for logic, so not memory. It also has wide multiplexers and access to the carry chain, and this is used for about 25% of the resources in the FPGA. Finally, the SLICE-X, which is a simpler slice configuration, supports logic only and is about half the device. The LUT can only be used for logic, not memory. There's no muxes and carry logic. Most customers don't use as many LUTs for distributed memory or the shift register LUT as you might think. So this segmentation of the functionality does not usually have a performance impact, but saves transistors for other purposes that will be more beneficial to the user. Also keep in mind that the implementation tools will lay your design out onto the die, so understanding which slices are an M, an L, or an X is not really pertinent to you. All we wanted to do was explain that they are different and show you how they are different. The input-output blocks, or IOBs, interface between the FPGA and the outside world. They are shown in this diagram on the periphery of the die. IOBs are grouped into IO banks located on each edge of the device. The IOBs contain registers and some specialized resources, but the main purpose of the IOBs is to clock data in and out of the FPGA. In fact, using the registers to clock data in and out of the device is the fastest way to move data in or out. Besides the registers, the IOBs contain interface logic that is designed to translate the internal voltage domain of the FPGA to whatever I/O stand you're using outside the FPGA. This saves you from having to add all the necessary interface logic outside of the FPGA. This requires that each bank share a common power supply for inputs, called a VREF, as well as the power supply for the outputs, or VCCO. These voltages vary by I/O standard, and the Spartan-6 supports many I/O standards. Fortunately, many of these standards can share the same power supply, so one of the things to keep in mind is we want to keep compatible I/O standards in those same banks, or group them into banks. Spartan-6 has 4 to 6 I/O banks, and this will depend on the device density, and each I/O bank has between 30 and 83 I/O pins, and of course that will vary by density and package options as well. The versatile Select I/O resource was first introduced with the Vertex family of FPGAs several years ago. It has been enhanced with every new product family ever since. I/O standards have been added and selected to support what our customers require. Spartan-6 FPGAs support over 40 I/O standards, including those you see listed here. But check the datasheet to see if your I/O standard is supported. That'll have the complete list. Note that there are memory-specific standards of various classes, differential standards that require 2 I/O pins to receive or transmit signals. The differential signaling standards include LVDS, LVPECL. The single-ended I/O standards include LVCMOS, SSTL, and HSTL. The Select I/O feature allows direct connection of the FPGA pin to external signals of varied voltages and thresholds. This optimizes the speed-noise trade-off and saves you from having to place interface components onto your board. All the dedicated interface logic already exists and can be selected on a pin-by-pin basis. However, note that to mix different I/O standards into the same I/O bank, you must be aware of the I/O banking rules. These rules apply because each I/O bank shares the power pins for each of the input and output pins in the bank. Specifically, the VREF powers the input circuitry and the VCCIO pin powers the output circuitry. So whichever I/O standard you group into each I/O bank, make certain that the input pins have the same VREF and the output pins have the same VCCIO. Now, this is easily planned with the pin ahead utility that's included with the ISE design suite. This slide is just trying to show you how differential pins work in Xilinx FPGAs. Each pin in the device can be configured as single-ended, and most can be configured as differential. The differential transmitters are available only in the top and bottom I/O banks, specifically Bank 0 and Bank 2. The differential receiver and the receiver termination is available in all I/O banks. Note that these limitations have an impact on your pin layout, so be sure to plan on laying out your differential transmitter pins properly and early in the design flow.